Welcome, everyone. We're delighted to have you here. We've had so many great sessions. I'm Erin Gray with Num Focus, and we are delighted to have you here. We've got a great session coming up with Dr. Alan Downey. Many of you may know Dr. Downey, but if you don't, he's the principal data scientist at PyMC Labs and professor emeritus at Olin College. So we've got a great session ahead. Just a reminder on this one. This is a longer session and we will need the full time. So we're really excited. Please put your questions or comments in the chat. We'd love to have interaction as we go throughout the session today. Dr. Downey, I'm going to turn it over to you. So glad to have you here today.
Great, thank you very much. And let's get started. I'm going to set up a few things here. There are some resources here on AirMeet. If you want to grab the slides for today and the notebook for today, there are links there. I'm also going to give you a link to the slides, and you can use that to get to all of the other resources. So with that, let me get to the first slide. Okay, welcome to Bayesian Decision Analysis with PyMC. As Erin said, I'm a principal data scientist at PyMC Labs, which is the group that produces PyMC, an open source tool for doing Bayesian statistics, and also provides consulting for people who are working in Bayesian statistics. I've been with PyMC Labs for about 2 years. Prior to that, I was a professor at Olin College, which is here in Massachusetts. While I was there, I worked on a book series, including Think Bayes. So that's one of the resources that I'll recommend if you want to learn more about Bayesian statistics. But today is going to be an introduction where my goal is to get the most important ideas across as quickly as we can. So 90 minutes, I'm going to show you what I think are the most powerful applications of Bayesian statistics. I want you to see what the value proposition is immediately. And in particular, I think Bayesian statistics are useful for helping to guide decision-making in a way that classical statistics is not always helpful. And particularly, the tool that we're going to be using is PyMC. We'll do it in three parts. And we'll have a little bit of a break between them. So you'll have a chance to stretch out. And I will also try to answer some questions in the chat. While I'm presenting, I won't be able to answer questions, but I'll use the breaks to do that. As I mentioned, the resources are all on AirMeet, or if you want to use this tinyurl.com and go to Dow25BDA, that will take you to these slides, and the slides have all of these links. So there's a link to the GitHub repository that contains all of the materials. You don't need that for the workshop today, but if you want to come back to it later, all of the notebooks are there and a little bit of additional material. The notebook that we're going to use today is this first link, the one that says no solutions, because that's the one where you are going to fill in the solutions to the exercises as we go along. If you don't want to do that, you don't have to. The other link will give you the notebook that already has the solutions in it. And if you get stuck at some point or you fall behind and you want to look at the solutions, that's available for you. But I encourage you to play along because I think you will learn more, stay focused. It's just more fun if you do the exercises. So if you want, go ahead and follow that link and get the notebook started. I'm just going to give you a brief introduction to part one, and then we're going to jump into the notebook. So part one is about the Bayesian update. And what the update means is that we're going to start with a prior distribution that represents what we believe before we see the data. And we're going to compute a posterior distribution that represents what we believe after we see the data. This is the fundamental idea of all Bayesian statistics, so that's where we're going to start. Now, let's jump into the notebooks. This is what the repository looks like. I am not going to run on Colab just so that I have a little bit more real estate to work with, and I hope that my screen will be more readable. I'm going to go into the notebooks folder, and the notebook that we're going to run today is the one that says 01 beta binomial, and you will see very soon why it is called beta binomial. I'm going to open up that notebook. If you are already running this on Colab, you have seen the introduction here, and the first cell, which is going to install one of the libraries we need, which is called Prelis. Most of the libraries that we need are already on Colab, so you don't have to install them. And I already have it in my environment, so I don't have to install it. But if you're running in a different environment, you will see a bunch of text that comes out there as it does the installation. The next cell is going to import all the libraries that we're going to use. Some of these might be familiar to you, like NumPy and Matplotlib and Pandas. The ones that might be new, we're going to use PyMC. That should come as no surprise. We're going to use Prelis, and we'll see soon what that's for. And we're going to use RViz, which is a tool for visualizing the results of these kinds of Bayesian models that we're going to do. So I'm going to run that cell. I'm also going to run this. This just makes the figures a little bit smaller, which is going to help with the screen real estate. And then the last thing is to make NumPy print numbers as just numbers rather than what NumPy 2.0 does. All right, let's get into our first example. And I need to experiment a little bit with screen size. I hope this is nice and readable, but of course you have the notebook as well. So we're going to start with a motivating example, which is digital marketing. And this is the classic A/B testing, where you have two different versions of an ad or a web page or whatever it is that you're presenting to customers. And you think that some of them are going to be more effective than others at getting customers to click on something. Or in the context of like a medical test, it could be the outcome of a treatment, whether it's effective or not, a public policy intervention. The same logic here applies to anything where there's a binary outcome, where a customer either clicks or they don't, a patient either gets better or they don't. So what we want to estimate is the percentage of effectiveness. So for an email campaign, it would be something like a response rate that says how many people are going to click on this offer. So I'm going to start with not just A/B testing. We're just going to do A testing. We're going to start with a single example, which is we send out an email campaign to 100 people, and 8 of them have accepted the offer. So the conversion rate that we observe in the sample is 8%. And what we want to do with that data is estimate what we think is the probability that someone responds to this email. And we want to know how confident we are about that estimate. So we're going to put bounds on the precision of that estimate. And we want to make predictions that say, if we send that same email out to 100 people, how many of them will respond to the next round of this campaign. I'm going to start by creating a dictionary that's going to keep track of the results. So n equals 100 means that I've sent the email 100 times. K equals 8 means that 8 people responded. Now, to answer this question, we are going to use the beta binomial model. That's why the notebook is called beta binomial. And it has two parts. The beta distribution is going to represent what we believe about the conversion rate. So it's somewhere between 0 and 100%. And this distribution is going to represent where in that range we think is most likely and the shape of that distribution. We're going to use the binomial distribution to represent the data. So that will be the distribution of outcomes, which in this case is the number of responses. So I'm going to start by showing what these distributions look like. So no Bayesian statistics yet. We're just going to explore distributions. The beta distribution is defined between 0 and 1. And it has these two parameters, which I've chosen as 2 and 5. They're called alpha and beta. And I'm using this library called Prelis to graph this distribution, and we're going to do some other work with this distribution. So from Prelis, I'm importing this beta object. I instantiate a beta object with these parameters, 2 and 5. And with those parameters, the distribution of this mean, the mean of this distribution is about 0.28, so 28% response rate. But it's very uncertain. If you look at the shape of this distribution, you can see that all the values from 0 up to about 0.8 are possible. The most likely value is 0.2. The mean is 0.28. And what this represents is the belief that the conversion rate is probably less than 0.8, most likely somewhere around 0.2, unlikely to be 0.9 or 1. But also this distribution is really wide because it says, values all the way down to 0 and all the way up to 0.8 are possible. So this is a prior distribution for what we believe about the conversion rate, and it's a weakly informative distribution in the sense that it constrains the values a little bit, but really not very much. We're going to talk in just a couple of minutes about where these prior distributions come from. So if that's your first question, hold on to it for just a minute. We'll come back to it. All right, so that's what we believe about the conversion rate. And now to talk about the binomial distribution, let's pretend for just a minute that we know the conversion rate, that we know that it is exactly 0.2. In real life, we don't know that, but again, for this example, if we know that the conversion rate is exactly 0.2 or 20%, and we send 50 emails, the distribution of the number of responses is a binomial distribution with those parameters. It has n equals 50 and p equals 0.2. And again, I can use prelis. I'm going to get this binomial object, instantiate an object with those parameters. And with those parameters, the mean is 10. And that you probably can compute that one in your head. If you send out 50 emails and the probability of success is 0.2, then the expected number of successes is 10. And the distribution of those successes looks like this. It is centered at 10, but it goes all the way down to about 3 before it becomes quite unlikely, gets up to about 18 before it becomes unlikely. So the range of outcomes is still quite wide, but things from about 21 on up are very unlikely. So this tells us what the likelihood of the data is for a given value of that conversion rate. And those are all the pieces that we need in order to do a Bayesian update. So again, we're going to start with a prior distribution that represents what we believe before we see the data. We're going to compute a posterior distribution that represents what we believe after we see the data. Now, there are several ways to do this. And one of them is sometimes mathematically, you can just compute what that posterior distribution is. And in fact, for the beta binomial model, we can. So there actually is a mathematical analytic solution to this particular example. But the vast majority of Bayesian problems don't have a simple mathematical solution. So we end up solving them computationally. One way to do that is by using a grid approximation where you replace all the continuous things with discrete things. That's mostly the approach that I took in Think Bayes. So if you want to know about grid methods, Think Bayes is a good place to look. MCMC, Markov chain Monte Carlo sampling, is the most common method with non-trivial Bayesian models. And that's what we're going to use today. So we're going to use the PyMC library, which I mentioned, and it provides algorithms for doing MCMC sampling. So our job now is to specify the model using the tools of PyMC, and then PyMC will provide these algorithms for generating a sample from the posterior distribution. And to see what that looks like, we're going to do the first exercise, which is to fill in this model. So I've provided you with the outline of a basic PyMC model. And in particular, it starts here with pm.model. And that's the function that creates an object that represents your model. And we're going to add pieces to this by defining variables inside of this with statement. So if you are comfortable with Python, you have probably seen context managers. This with statement creates a new context manager. What that means is that every time we create a new PyMC object inside of this with statement, that object will automatically become attached to the model. And we'll be able to add pieces to the model and connect them to each other just by creating objects inside of this context manager. And part one of that is to create an object that represents the prior distribution. And now here's where you get to do some typing. I'm going to show you what this looks like. You should type along and then try it out. One of the reasons that that's useful is that you might make some mistakes, and if you do, debugging them will really help you learn about what's going on. Up to a point. If you make a mistake and you really can't recover and you're just confused and it's not helping you learn, go to the solutions, copy that over, and hopefully that will get you unstuck. So a little bit of difficulty is really good for learning. A lot of difficulty is just frustrating and not productive. All right, so we're going to use pm.beta, which is a function that's going to create a new object that represents the beta distribution inside of this model. And the arguments that we need to provide are first a string. This string is going to be the name of this object inside of the model. And by convention, I am almost always, when I create one of these objects, going to use the same string as the first argument as the variable that I'm going to assign this to. It doesn't have to be, but there's no good reason to break this convention, and it's certainly a lot simpler if the name of the thing inside the model is the same as the variable name that you've assigned it to. Now, I need parameters for this beta distribution, and I'm going to use the same parameters that I used in that example we were just looking at. So 2 and 5 create a beta distribution that has that shape we just saw. And what it means is that I think for most email campaigns that are like this one, the conversion rate is typically less than about 50%, but I'm very uncertain about what it will be. So I'm choosing a prior distribution that is really wide, because that means that the data will speak for themselves. The data will tell us where in this range the conversion rate actually is. So that's part one. We built a prior distribution. We created this beta object that's called conversion rate. Now we're going to use a binomial distribution, and similarly here, pm.binomial is the function that creates a binomial object inside of this model. I'm going to call it OBS, which is short for observed, and that's again a convention to give a name to this object that reminds me that this is the observed data. So this isn't a prior distribution. This is the observed data, and it's called a likelihood because what's being computed here is the likelihood of the data for a given value of the conversion rate. So I'm going to fill in, instead of this 0, we're going to connect these two objects together by putting conversion rate here. And what that means is that this value that gets drawn from a beta distribution is used here as the p parameter of a binomial distribution. The n parameter is the data. This is the capital A bracket n. So going back to that dictionary that we created, this is the number of times that we've attempted the email campaign or whatever it is. And similarly, the observed data is also going to come from that dictionary, and that's going to be the k value that gets pulled out of that dictionary. So this says we sent n emails. We think that the conversion rate is this value that we drew from a beta distribution, and the observed data is the k successes. And that's it. That is the complete specification of the model. So if you execute this cell, it will build the model. And if you have any typos or if there's anything broken, you might get some error messages. If so, compare what you typed with what I have here on the screen. But since I didn't get any output at all, that means that the model has been successfully built. And we can use this function called model2graphviz to see what the model looks like graphically. And what it shows is one oval for each object that we created. So we have conversion rate. It's being drawn from a beta distribution. We have the observed data. It's being drawn from a binomial distribution. This is gray to indicate that this is observed data. So this is a likelihood and this is a prior. And the arrow is showing us what the relationship is between these objects, which is that the conversion rate here gets used as one of the parameters of the binomial distribution here. Okay, So we've created an object, and now we're going to start drawing random samples from the object. So the function that I just ran is called sample prior predictive. And what it's going to do is it's going to generate a sample from the prior distribution. It is also going to generate a sample from the prior predictive distribution, which we are not going to talk about today. So forget about prior predictives, but we will talk about priors. What this means now is that I can plot the prior distribution from that beta distribution. And I'm using this function, which is called plot prior. It calls arviz. So AZ stands for arviz, and it's going to provide the functions that we are going to use to visualize distributions today. Now, the function that we're using is called plot posterior, but then we call it with group equal prior to say that we actually want to plot the prior distribution. I find that confusing, which is why I have wrapped this whole thing in a function that is called plot prior. And what this is showing is the distribution of the sample that we just drew from the prior distribution. Now remember, when we did this analytically, I'm going to scroll up. This is what the distribution, that beta distribution, looks like if we compute the PDF analytically. And this is what it looks like if we draw a random sample and then plot the distribution of that sample. So they are approximately the same. They have roughly the same location and spread, but the sample is a little bit lumpier because of random variation. So that's my prior. And this is useful when you are building a Bayesian model. It is a good idea to sample and plot the prior distributions as a way of checking your model, making sure that you have specified the model the way you intended to. Now, we are going to run this function, which is called pm.sample. And this is kind of the whole why PyMC exists, which is this function which is going to compute a sample from the posterior distribution of beta given the data that we have observed. I'm going to run it. And when it runs, we're going to see some interesting information come up on the screen. So the first thing is that it tells us that it is initializing the NUTS algorithm. NUTS is the no U-turn sampler. That's one of the algorithms that's built into PyMC. And it is kind of the workhorse of a lot of Bayesian sampling. It's going to run 4 chains. Remember that this is called a Markov chain Monte Carlo sampler. So it runs 4 chains. That is useful as a way of checking that the results are reliable because the 4 chains should look very much like each other. And if they don't, that's one of the ways that we can detect that things are going to go wrong. Now, I'm going to talk very little today about how to diagnose Bayesian models because the models we're using today, the beta binomial model, the sampler tends to work really well. We don't have to do a lot of checking. It also runs pretty fast. Yours might be just a little bit slower on Colab. And actually on Colab, you probably got 2 chains rather than 4, but totally fine either way. What's important is the posterior distribution. So now we're going to use this arviz function called plot posterior. We're going to take the result from the sampler, which is called idata1. The reason it's called idata is that it contains inference data. It contains the data about the statistical inference that we just did. And if I plot the posterior distribution, this shows me what we should believe about the conversion rate after we see the data. Now remember that in that really wide prior distribution, the mean was 0.28. And that says, yeah, we think that there are email campaigns where the response rate is 28%. But what we observed was only 8%. So we're pretty sure that the posterior mean is going to be less than the prior mean because the data is going to pull it down. The data is providing evidence that the actual response rate is lower than the prior mean. And sure enough, it is. The mean of this posterior distribution is 0.093, which is 9.3%. And the width of the distribution, most of the data falls within this 94% HDI. HDI stands for the highest density interval. This is analogous to a confidence interval in classical statistics. But what this is telling us is in the posterior distribution, this interval covers 94% of the posterior probability. And what it says is that the conversion rate is probably between 0.045 at the low end and 0.15 at the high end. So somewhere between 4.5% and 15%, and the mean again is 9.3%. So that is the posterior distribution, and that is a Bayesian update. We've done it. We started with a prior, we used data, we computed a posterior distribution that represents what we believe about the parameter, the conversion rate, after we see the data. So that's key. That's the first part of what we're doing here. The other key thing that we've seen so far is how to build a PyMC model that specifies the priors and the likelihood of the data. And again, in this example, the prior is the beta distribution and the likelihood is the binomial distribution. And then we used pm.sample, and I set it in a nice big font here because it's the most important part of the whole thing, which it generates a sample from the posterior distribution. So we've done it. We've done a Bayesian update. To show all of that in one figure, I'm going to take the two things that we computed. Remember, we have prior iData1, which contains a sample from the prior distribution. We have iData1, which contains a sample from the posterior distribution. And then we put them together. That's what this extend function does. It puts them together into one object. That allows us to call this plot dist comparison so that we can see everything in one place. And in particular, this graph here at the bottom, I think is the key visual idea about what's going on. The orange line is the prior distribution, and it's super wide. It says any value between about 0 and 0.8 is almost equally likely. Yeah, we think, some of the ones that are around 0.2 or 0.3 are more likely. So what that represents is great uncertainty. And now, having seen the data, we get the blue line, which is the posterior, which is much narrower. And that is doing what you would expect data to do. It's providing information, it's giving evidence, it's making us more confident about the actual conversion rate for this particular email rather than just any old email. So that's the Bayesian update. And again, there's a summary there that will remind you. Now, I skipped over an important thing and I want to come back to, because this is the question that every time when people learn Bayesian stats for the first time, this is honestly, I think, the thing that bothers people the most, which is, where did that prior distribution come from? It seemed like you just made it up and it was totally arbitrary. In the case of that first example, it kind of was. It was a weakly informative prior. It's based on some domain knowledge, which is, email campaigns, you're not going to get an 80% response rate to anything. So we have some prior knowledge that tells us that most response rates are relatively low, but we didn't choose a super narrow distribution, a super narrow prior, because we wanted to let the data speak for itself. However, that's not always what you want to do. And here's an example that demonstrates it. This is one of the examples from ThinkBayes. I call it the rookie problem. And here's the idea. So a new player has just joined Major League Baseball. They're playing in the first game that they have ever played. And they come up to bat 3 times and they get 3 hits. So the observed success rate is 100%. And now your question is, well, what do we think their actual batting average is going to be over the long run? Because nobody always gets a hit. In Major League Baseball, typical batting averages are between 170 and 310, which is this kind of weird way of saying it's between 17% and 31%. So nobody hits 100%. So here's the challenge. We have this data that says that the player went 3 for 3. We want to make a posterior estimate for what their long-term batting average will be, like their probability of getting a hit. So we're going to use exactly the same model. This is the same model we had before. It has the beta distribution here as the parameter. It has the binomial distribution here as the likelihood of the data. And sorry, I meant to say here that the beta is the prior, the binomial is the likelihood. And what we're estimating is a batting average. And I sampled from the prior and I sampled from the posterior. And now we can see what those look like. The prior is the same as what we had before. And what it says is we think that batting averages could be anything from 0 up to 0.8. And the posterior distribution says that for this rookie who went 3 for 3 in just one game, we think that their batting average is likely to be about 500, 0.5, 50% chance of getting a hit, could be as high as 0.77, might be as low as 0.21. So if you're familiar with baseball, you know that nobody has a batting average that's 50%. Nobody bats 500. So this is an unreasonable posterior estimate because honestly, we started with an unreasonable prior. We only had a small amount of data, so we didn't really have enough data to cancel out the bad prior. In that case, when you have small data and the results are very sensitive to your choice of a prior, what you really should do is find more domain knowledge to tell you what do we really know about the world and use that background knowledge. So that's what we're going to do. What I've done here is estimated the actual mean and standard deviation of batting averages in Major League Baseball. The average player in the major leagues bats about 240. The standard deviation is about 0.07. So it gets, at the high end, it's about 310. At the low end, it's under 200. So here's what we're going to do. We're going to loop back up in the notebook, and we're going to make a better prior, and we're going to make it with these parameters. So what I've computed here with this function called compute params, it takes the mean and standard deviation that I want, and it computes the alpha and beta parameters that I'm going to use as part of the beta distribution to specify a better prior. So here's the second exercise that we're going to do. We're going to loop back around, and instead of 2 and 5 for the parameters, we're going to replace them with, let's say, 8.7. I'm going to actually write this down. I could copy and paste it, but I'm going to write it down. 8.7 and let's say 27.5. So scroll back up and find where we defined the rookie model. So find this part of the notebook. And here where we specify the prior, instead of 2, 5, which makes this really wide distribution, we're going to use 8.7, and 27.5. And this only has to be approximately right. I'm going to, again, run the two samplers, and we'll see what the new prior distribution looks like with those parameters. So sure enough, the mean is now 0.24, and the range is much less wide than it was before. And this says probably, the person in Major League Baseball with the worst batting average is about 100. The best ever is about 400, and typically it's about 240. And now, if you look at the posterior distribution, this will be what we think about a rookie who goes 3 for 3. And what it says is the mean is about 0.3, and the range is from about 0.16 up to 0.43. And notice that the 0.3, is a much more reasonable number than the 0.5 we were getting before. There are actually people in Major League Baseball with a batting average of 300. That's good. It's definitely the high end of the range. And going 3 for 3 in one game might not convince me that this rookie is going to hit like that all the time, but in fact, it could be quite a bit lower. All right. So that is the end of this example. And really the point of it is if you have small data and the results are very sensitive to the choice of the prior distribution, you want to make sure that you are using as much background knowledge as you have to choose a prior that genuinely represents what you believe before you see the data. If you have a very large data set, it often doesn't matter. With a very large data set, you can afford to use a weakly informative prior, and the result probably won't depend very much on the prior at all. This example also demonstrates shrinkage. I'm going to come back to that later because we're going to see more of that in one of the future examples. So that's part one. That's the Bayesian update. And if you only remember one picture from part one, you should remember this. This is what it looks like when you go from a really wide prior to a narrower posterior. And then one more time, it represents what you believe about the data, about the parameter after seeing the data. We are going to take a 5-minute break. We will come back at 11 minutes past the hour, and we will jump into part two, which is about Bayesian A/B testing. During the break, I'm going to look at the chat and see if there are questions to answer. I'll see you in 5. Okay, let's get started again. Part 2, as I said, is about A/B testing. Let's get back to the notebook. We'll get right into it. You'll notice that the title is Bayesian Bandits, which is a strategy for making decisions that are based on your posterior distributions. So we'll see that in just a minute. So we're going to take the example from last time and extend it to A and B testing. And in particular, I'm going to create a dictionary here that represents one of the versions of this email campaign where we know that the actual conversion rate is 10%. And again, in reality, we don't typically know that, but for the purposes of the simulation, I'm going to say that that's the conversion rate. And I'm going to start it out with n equals 0, k equals 0, meaning that we have never sent this campaign to anybody. To run, or rather to simulate a campaign, I'm going to use this function. Notice inside this function, we have pm.binomial.dist. And we've seen pm.binomial. That's the function that we used to create an object inside of a model. With this .dist, what I am creating is an object that we can use as a random number generator. So I'm creating a binomial distribution, which for a given value of n and a given value of p, will simulate n trials with the given probability and return the number of successes, which is what we've been calling k. So each time we call this draw function, we get a value of k, and we're going to update the dictionary by incrementing n and incrementing k. So create the dictionary, create the function, and now we can simulate sending 100 versions of the email out to 100 people. And when I ran it, I got k equals 9. When you run it, you're going to get different values. And I think that's useful because we're all going to see different versions of this, but we will also see that in the long run, they will converge to the same destination. With the data that we just computed, I'll do the same update that we did before. So this is exactly the same model. This is going back to the beta distribution with these parameters. So this is the wide prior. And I'm using this dictionary to get the values of n and k. So I now have a posterior distribution for A. I am now going to compute a posterior distribution for B. I'm going to create a new dictionary for B where P is 0.15. So B is actually better than A. And that's a key thing that I want you to remember. So this is like doing a medical test where we have the old treatment A, we have the new treatment B, and B is actually better. And what we want to do is gradually learn how much better each of them is. So I'm going to run another campaign. I'm going to send out another 100 emails, and I'm going to send 80 additional emails for A and 20 emails for B. And so now for A, we have 180 trials, and for B, we have only 20. And that's deliberate. I want to show you how this model behaves when you have more data for A than you do for B, because that's how it usually is. When you start something new, you have lots of data for the old thing, not so much data for the new thing. And now we're going to run this version of the model. I'm calling it model AB, and it simultaneously estimates the posterior distribution for both A and B. So I've got 2 copies of the prior and 2 likelihood functions being updated with the data for A and the data for B. And what that means is that in my posterior distribution, we're going to have 2 samples instead of 1 for the conversion rate of A and the conversion rate of B. And if I plot the posterior, we can see both. Now, in my example, B did really well and A only did okay. So the posterior mean for A is only 0.11. The posterior for B is 0.26. Neither of them is exactly correct. Remember that for A, the correct answer is 0.1. So that's pretty close. And for B, the correct answer is 0.15. So right now, because I have such a small data set, this is kind of like the rookie problem, that we think that B is better than it actually is. So there are a couple of things now that we can compute using these posterior distributions. And I'm going to use this extract function to pull the values out of this iData object. And then I'm going to convert them to NumPy arrays. And I'm doing that because I'm going to use some matplotlib functions. And actually, we're also going to use this plotkde function. And this is coming from rviz. So this is showing the posterior distributions for both A and B. And this represents 2 things. One of them is we think that B is better, but because the sample size for B is so small, the posterior distribution is still quite wide. And what that means is that we cannot yet rule out the possibility that A is actually better. These 2 distributions still overlap, which means we think that B is better, but we're not sure. And here now is the key to the whole thing. What should we do? If we want to send out the next batch of emails, there are a couple of things that we could think about. We could say, well, we think that B is better, so let's just throw away A, and from now on, we will use B all the time. That's one option. Another option is to say, well, we have not yet proven that B is better than A, so until we have really strong evidence that we know for sure that it's better, then we're going to keep sending out A and B, and maybe we would go 50-50. Bayesian statistics gives us a different approach to this question. So rather than asking a binary question, like which one is better, A or B, we're never going to answer that question. We're always going to express our beliefs in terms of probabilities. So we're going to compute the probability that A is better than B. And there are a couple of ways to think about that. One of them is we can compute the differences, and we can plot the distribution of the differences. And right now what this says is we think that B is better, and we think that the difference is 0.15, but it's still quite wide, and in fact, it could be negative. So we could be wrong. Now, again, when you run this, you're going to get different numbers. And in fact, if you are a little bit unlucky, it might be the other way around. So some percentage of you are probably a little bit puzzled right now because given the data that you generated, you might temporarily think that A is better. Now, we're going to go back in a minute. We're going to generate more data, and eventually your data will probably convince you that B is in fact better. But for now, if it's the other way around, don't worry. That is a thing that's going to happen. But for me, I can now compute, well, you can too. You can compute the probability that A is better than B just by counting the number of times that the sample from A, the posterior distribution from A, exceeds the posterior distribution for B. So that's here. That's the probability of superiority for A. Here's the probability of superiority for B. I didn't really have to compute both of them because they add up to 1. But what this says is, with the data that I've seen so far, I'm 97% sure that B is better. And now, what should I do? And the answer that we're going to use is Thompson sampling, which is the idea that we will send out the next batch of emails. We'll send them A and B in proportion to the probability of superiority. And that's it. That's the whole idea. So we are 97% sure that B is better, and therefore we're going to send 97B and only 3A. So we're not going to completely discard A. We're not going to completely switch to B. But in this case, almost 97.3. And I'm going to run the campaigns again. So run those two cells, and it will simulate the next round of the campaign with the proportions that we just computed. And then we're going to loop back around and run the whole thing again. So let me pause for just a second and give you a chance to run all that. And again, the numbers that you're going to see are different from mine, but after we do a couple of iterations, they should start to converge. All right, let's go back up to the top. Now, in my example, B got a little bit lucky. And so the difference between B and A looks a little bit bigger than it is in reality. So I suspect that when I do my next iteration, A and B are going to come a little bit closer together. In particular, this number, the 0.26, I think that's probably going to come down based on the new data that I've observed. So here, where it says loop back to here, that's where you should loop back to. If you've run the new campaigns, you have updated these two dictionaries for A and B. And so if you run this sampler again, it will compute the new posterior distribution that's based on all of the data. So we're coming back and starting with the same prior again and doing an update with all of the observed data from what's currently now 2 rounds of the campaign. I'm going to run the sampler. One note I'll make is that for this model, the runtime does not depend on the sample size. So it is just as efficient to go back and do all of the data at once. We could have done an incremental update, but for this model, there's really no advantage to doing that. Okay, so here are the posterior distributions after 2 rounds of the campaign. We can see that the estimate for A is still 0.11, and that is still quite close to what we know is the actual value, which is 0.10. And B has come down a little bit. Remember, what is it? Was it 23 before? It was like a little bit too high. Now it's 0.17, and that's quite close to the reality, which is 0.15. And if we look at the new posterior distributions, particularly the one for B has become narrower. And it is because we now have more data. So in general, when you get more data, your posterior distributions will get narrower, and that represents greater precision in your estimate of the conversion rates. I can look again at the distribution of the differences and the probability of superiority, and we still think that B is better. The probability of superiority is about 93%. That came down a little bit because our estimate was a little bit too high previously. And so for the next campaign, if we do one more round, this time we're going to send out 93 Bs and 7 As. And this is kind of like a compromise. This is saying, if I think B is better, I do want to send more Bs, because if I don't, if I like stayed 50-50, I would be wasting effort on A when I think it's probably not the best option. But as long as I'm not certain that B is better, I probably want to keep poking at A just a little bit until eventually you get to a point, and maybe this next round we'll see it, which is if you loop back around again and run the sampler, plot the posterior distributions, they will get narrower and narrower. They will converge on the true values, and so they will overlap less and less. And eventually you'll get to a point where the probability of superiority is close enough to 0 and 100% that you could say at that point, okay, we're never going to send A again. We're convinced that B is better. Or in medicine, you say, look, we're not going to use that old treatment anymore. We have a new treatment that's better. So that's it. If you run a few iterations, you should eventually converge to results that look like mine, unless, just by random sampling, you get a little bit unlucky. So to wrap up part 2, I think a key idea in Bayesian statistics is that we almost never ask binary questions. We don't ask, is A better than B? We almost always want to estimate what is the difference between A and B. So you could answer that with a distribution of differences, or the probability that A is better, and you would answer that with a probability of superiority. Second thing that we saw is Thompson sampling. And this is the idea that if you have imperfect information and you have to make a decision about what to do next, this is a way to take advantage of what you know without exaggerating what you know. So you're always choosing among the options in proportion to the probability of superiority. And this is a way of making a principled balance between exploration, which is finding out more about your options, and exploitation, which is taking advantage of the information that you already have. If you remember just one picture from this part, this is a good one to have in mind, because this is a situation you will often be in, where you have a lot of information about the old thing, not a lot of information about the new thing, and so you have these overlapping distributions. And it's that overlap that is, in some sense, the problem. That overlap represents your uncertainty about which one is better. Okay. That was, I guess, a little bit shorter than part 1, but I do want to take another break because I think it's just important to rest, give me a chance to answer some questions, and we'll come back. So we'll take another 5-minute break, and that'll be 32 minutes past the hour. And again, I'm going to answer some questions. I'll see you in 5. Okay, let's get back to it. So part 3 is about hierarchical models, and this is often a kind of advanced topic that you would not get to in 90 minutes, but I wanted to get to it because I think it really demonstrates the power of Bayesian models. And in particular, for this example, hierarchical models learn at 2 levels at the same time. So every time you send out a campaign, you are learning specifically about those options like A and B, but you are also learning about email campaigns generally. And that allows you to generalize the data that you have, to make a prediction about something in the future that has never been observed. And it also allows you to share data between different observations. I'm going to explain what that means by looking at this example. Now, there's one thing that we need to do before we can get into the hierarchical model, which is that we need one more distribution. And we're going to use a gamma distribution that is going to be a hyper prior. And a hyperprior is a prior distribution that describes the parameters of your prior distribution. So we're going to use this gamma distribution. I'm going to use Pralese again to create a gamma object, and I'm going to give it this alpha and beta. So alpha and beta will be the parameters of the gamma distribution. And sorry for all the Greek letters, but that's what it is. The mean and the standard deviation are 2 and 0.5. And here's what it looks like. The gamma distribution is a positive valued distribution, so it's only defined for 0 on up. In this case, the lower bound is around 0.5. Goes up to about 0.4. None of that might mean very much yet, but I'll show you soon why I chose that particular parameter. Now, let me set up the example. So we're going to continue with A-B testing, although in this case it's going to be A versus D. A is the same A we've been working with all along, where the actual probability of success is 10%, 0.1. D is this new version. It's even better than B. The probability of success is 0.2. And I'm going to do the same kind of different sample sizes that we saw before. So A is the old thing that has now been sent 200 times. D is the new thing that has only been sent 10 times. So really small distribution. And I'm just going to run these again to make sure I've got everything good. And now we are going to run this model to compare A and D. This is exactly the same as the previous model where we compared A and B. The only difference is here. I'm using that new data that I just generated. The reason I'm running this model, this is still not hierarchical. We are going to start with this. We're going to make it hierarchical in just a minute. So let me run it. Sample from the posterior distribution. And here's what the posterior distributions look like for A and D. And I've added these dashed lines to show where the actual values are. So again, for A, it's 0.1. For D, it's 0.2. And we can see in both cases that the posterior distribution covers the actual known value pretty well. We're going to use GraphViz again to see what this model looks like. And we can see that we have a prior for A, a likelihood for A, prior for D, likelihood for D, and they are not connected to each other. There are no arrows from one side to the other. And in fact, there is no mathematical connection between the two. These are completely independent models. I ran them at the same time, but I didn't need to. If I split this up into two models, I would get exactly the same results. And that is a missed opportunity. We are leaving information on the table because when we send out version A, we are learning about A, but we are also learning in general about how successful these email campaigns are. Like in the question, somebody pointed out that really often response rates are more like 3%, not 10 or 20. I chose high numbers just because they're easier for us to think about. But let's say that we sent out a bunch of campaigns and the response rates were like 3%. We would very quickly learn that, yeah, no, actually 0.5 is extremely unlikely. So currently, we are leaving information on the table, and we are now going to solve that problem by taking this model. This is just a copy of the model we were just looking at, and we're going to make it into a hierarchical model. And we're going to do that by adding hyper priors. So this will be our hyper prior, and it is the hyper prior describes the parameters of the priors. So I'm going to have something called alpha, and it's going to come from that gamma distribution that we were just talking about. And I'm going to call it alpha. And I'm going to come back in just a minute and fill this part in. I need something called beta that's also coming from a gamma distribution. And again, I'm going to fill this in just a minute. And now I'm going to replace 2, 5 with alpha, beta. And this is kind of like in any kind of software engineering. If you see a program and there are these hardwired constants in it, you can replace them with variables. And that's kind of exactly what I'm doing here. What I'm saying is that for my prior distribution, I'm not going to assume that I know exactly what the prior is. I'm going to define these hyperpriors for alpha and beta, and I'm going to use them to adapt the prior as it goes along. This might sound really abstract. It'll make more sense in just a minute. Last thing I need is parameters for my hyperpriors. I'm not going to say too much about where this came from. I'm going to pick some magic numbers, and then I'm going to explain later why I chose the ones I did. Okay, let me just review my notes and make sure that I have put everything into this that I need. I think that's it. So if you are typing along, and I hope you are, again, you need to add alpha and beta. You're going to draw them from a gamma distribution with these magic parameters that I'll explain in a minute. And then here, where it used to say 2, 5, we're going to replace it with alpha and beta. And if you run this cell, it should make the model. If you don't get any error messages, that's good. And if you run the next cell, it will show the visualization of this model. And now, let's look at what we have. We have the observed data down here in gray. We have the prior here in the middle. And now we have the hyperprior up at the top. And notice now that we have arrows that connect the two sides. And what that means is that when we learn about A, that will affect what we believe about alpha and beta. And what we believe about alpha and beta informs what we believe about D. So information now flows from the left side to the right side through the hyperparameters. And similarly, it also flows from the right to the left. So when we do a sample from the posterior distribution, we are doing a simultaneous estimate of the conversion rate for A, the conversion rate for D, and the hyperpriors. They all get updated at the same time. So let's see how that goes. I built my model, visualized it. I have drawn a sample from the prior distribution so we can see those gamma distributions that I just created. Notice that the mean of alpha is 2 and the mean of beta is 5. And that's why I chose the parameters that I did, which is that this hierarchical model is going to be very similar to the previous model in terms of its prior beliefs, but it has this extra magical ability to learn simultaneously about A, D, and email campaigns in general. If I plot the prior distributions for A and D, they are not too different from what we had before. The mean is approximately 0.28, which is what it was before, maybe just a little bit higher here because of sampling. The width of the distribution is about the same as what it was before. So my purpose, my goal with this model is to make it as comparable as possible to the previous one, except that it's hierarchical. I'm going to run the sampler. It's going to take just a little bit longer to run because it's a more complicated model. And now we can look at the posterior distributions for alpha and beta, which are my hyperpriors, and the conversion rates for A and B. Alpha and beta have changed just a little bit, not a ton. So alpha, the prior mean was 2. The posterior mean is 1.8. For beta, the prior mean was 5. The posterior mean is 5.2. So they have changed a little bit, and that reflects what we learned about email campaigns in general. But we didn't have a ton of data, so we didn't learn a lot. They didn't change very much. For A and D, we have the usual posterior distributions. We've seen these many times. And in this particular example, they are not wildly different. They have been pulled toward each other just a little bit. So our estimate for A is just a little bit higher than it was in the non-hierarchical model. And for D, it's just a little bit lower. And in fact, the difference is so small that because of random sampling, that might not be exactly true for your random sample, but on average in the long run, A and D are being pulled toward each other just a little bit because the hierarchical model is saying that we think that email campaigns are like each other until we have enough evidence to convince us otherwise. So that's that. And if we look at the posterior distribution, we need to do one more thing. If you run this cell, you're going to get the same error message that I did, which is that we have not yet created this. I want to go back to the model and add one more thing. So again, we have our hyperprior. We have priors for the things that we actually observed. I also want to create a conversion rate new. Conversion rate new. And this is going to represent what we believe about an email campaign that we have never observed. So it's new in the sense that we've never sent it out. N is equal to 0. So it's going to be called conversion rate new. It's going to be based on the same hyperparameters that we have before. So again, if you're following along, add that to your model. But now we're not going to update it. There's no likelihood for this. And so the posterior for this will be based only on the posterior distributions of alpha and beta. And what it will tell us is, having seen data for A and D, what should we now believe about a new email campaign in the future that has never been sent out? So I'm going to update the model. If you visualize it, you'll see that the new variable has been added, and it has no observed data. So again, the posterior distribution for this will depend only on the posteriors for alpha and beta. I'm going to run the sampler again, and I can see the updates, same updates we saw before. And now, if you run this cell where we got the error, you will see this. And this represents what we should believe about something that we've never seen before. And notice that the posterior mean here is 0.26. It used to be 0.29. Before we did the update, it's 0.26 now. So having seen that the response rates for A and D were below the mean, our posterior belief about an unseen campaign has been pulled down just a little bit, not a ton. And again, we don't have a huge amount of data. Okay. One more thing I want to show you in this model. We have made a prediction about an unseen version of this email campaign. We will also make a prediction for what would happen if we sent another email campaign back out to A and D, sent out these two versions again, based on what we now believe about their response rates. And the answer to that question is called the posterior predictive distribution. We're going to answer the question, if we sent the same campaign out again, what is the distribution of responses we should expect to see? And we're going to use this function that is called sample posterior predictive. The result is another one of these iData objects. So we're going to take that result, posterior pred, and add it to the existing iData object. We're going to use this function called plot posterior predictive to see what that result looks like. What this says is, if we sent out A 100 times, we would expect on average to get 21 responses, but it could be as low as 10 or as high as 32. And notice that this is now a discrete distribution because these things are counts. They can only have integer values. And similarly for D, if I remember right, we only sent 20 of D, and so we should expect to get about 2.2 responses on average, but it could be as low as 0 or as high as 5. So that's often a Bayesian cycle, which is to use the data that you have to update your beliefs, and then use those beliefs to generate predictions about either a future unseen campaign or the same campaign again. All right. Let me pause for just a second. We're getting toward the end. And I want to see if we're going to have time for this example. Let me introduce this example. We might not have time to do all of it, but you have the notebook and you can finish this up on your time if you want to. If you run this cell, it's going to download some data, and it is the batting averages for everybody in Major League Baseball during the 2023 season. So we're going to continue that previous example, which was about advertising, and take this back to baseball. Because remember, we did the rookie problem. All right, I'm going to load up the data, and we can see that for every player, we have their name, what team they played for, the number of at-bats, how many times they attempted to get a hit. H is the number of actual hits that they got, and BA is their batting average, which is just hits divided by at-bats. So these are the people who had the worst season. Many of them only appeared in a couple of games and got a couple of at-bats. And then at the high end, the extremely high values are also generally people who only played in a few games. Here's what the distribution looks like. And this is where I got my prior distribution for the rookie problem. I used this data to see what are the actual mean and standard deviation of batting averages, and I used that as my prior. And this is the starting place. This is the same example that we had before, the same hierarchical model, and we're going to modify this to solve the baseball problem. So I'm going to show you one more feature of PyMC, which is that it works really well with arrays. So if you only have two things that you're comparing, then it's probably fine to have one variable for each of them. And maybe if there were three, you could have three variables. But I think there are, there it is, it's right there. There are 660 people who took an at-bat. We're not going to copy this line of code 660 times. We're going to make an array. So we're going to call this the player batting averages. And there's going to be one for every player in the league. So this variable is going to represent an array of batting averages. So player batting average. It's going to have these same alpha, beta parameters. The difference is that I'm going to give it a shape. And when I specify that the shape is the number of players, that's it. That's all we have to do in order to transform this model so that it works with an array of data rather than multiple observations. Oh, sorry, we also have to change the likelihood. So my likelihood here is just going to be my observed data. The conversion rate here is going to be the player batting average. In other words, this object that we just computed goes here. And now we need the data, and this will be the total number of at-bats, which is also an array. And this will be the total number of hits, which is also an array. So that's it. I wanted to make sure that we covered this so that you would be able to do this exercise. I'm going to run it just a little bit to look at some results, but then we're going to need to wrap it up. So take just a minute, finish typing that in, and you will have a nice new array version of this model. I'm going to run this cell, make sure I didn't make any mistakes. Looks good. I can sample from it. I notice this one now is taking a little bit longer. It is estimating more than 600 parameters. This is a 600 parameter model because we have one for every player, so that's 660, and then two more parameters for the hyperpriors. Here are the posterior distributions for alpha and beta. And now I want to do the same thing that I did before, which is to add a new player that doesn't get updated. So I'm going to have player underscore new coming from the same beta distribution. So in fact, I'm going to copy it. And this one doesn't get updated. So this is going to tell us what we believe about a new player who has never had an at-bat. Oh, I seem to have made a mistake. Oh, I have two things that have the same name. Can't do that. I need this string to, at the very least, it needs to be different from the previous one, but in general, it'll be the same as that variable name. Let's run it. Sample again. And now when we run this cell here, this will tell us what we should believe about a new player who has never had an at-bat. And there's that. And it says, we think that the mean is 0.24, could be as low as 0.11, could be as high as 0.39. And now if you want, you can check out some individual players. I've got this function that's called plot posterior for a specific player. So it takes this data frame, which is my original data set. It takes the iData, which is the inferred data, and the name of the player that you want to plot. And it extracts the posterior distribution for a particular player. It uses the plot posterior function. And it also plots a vertical line showing their observed batting average. And I picked a couple of examples of players with a small number of at-bats. So Chadwick Trump and Jared Walsh. I chose these two cases because they have the same observed batting average. In both cases, it's 0.125. But in the first case, it's based on only 16 at-bats and 2 hits. And in the second case, it's based on 104 at-bats and 13 hits. And what we see is that when the data set is small, this model does not take the data too seriously. So this person only hit 125, but the posterior mean is 200. So the model is kind of like the opposite of the rookie problem. Instead of saying, well, he had a good day, but I don't actually think he's going to hit 1,000. This is like the opposite. It says, look, he only had 16 at-bats. He only hit 125. But if I have to make a long-term prediction, I'm going to say 0.2. On the flip side, Jared Walsh has a lot of data. Same batting average, 125. He gets a little bit of credit, but the posterior mean is 0.15. And that's because in this case, Jared Walsh, we have enough data to say pretty confidently that his batting average is well below average. And in the case of someone who has only had a couple of at-bats, we don't have enough evidence yet, and so we don't move the posterior mean quite as much. There are a couple of other examples in the notebook, but I do need to wrap up. Just to summarize, hierarchical models make principled predictions for untested options. So a batter who has never taken an at-bat, an email that you have never tested, you can make a prediction for that. And you see this property called shrinkage that is what I was just talking about, which is that the model assumes that somebody is close to the mean until there is enough evidence to move them strongly in one direction or the other. So when the data set is small, you see shrinkage toward the mean. The batting average could get pulled down or up. When the data set is big, you have enough evidence to convince you that, yes, that person is actually very different from average. If you remember only one thing about this example, this is the picture to have. This is the likelihood at the bottom, the prior in the middle, and the hyperprior at the top. And it connects the two sides of the model by using the hyperprior to communicate information from one side to the other. If you want to continue with this, Think Bayes, I already mentioned, is my attempt to introduce Bayesian thinking. There's a free version of it at greenteapress.com. And with PyMC Labs, I am co-teaching a workshop coming up in January. So if you have the opportunity to join that workshop, it would be great to see you there. This session that we just did today is very much like the first session of that workshop. And then there are 7 more sessions that get deeper into everything that we talked about, new models, new applications. So if you are able to join that, I hope that you will. And if you would like to get in touch with me, here are some ways to do that. They are in the slides. Let me pop back over here, stop sharing for just a second, and I've got just 1 minute to say thank you very much. I hope this has been useful to you. I will take a few minutes after we wrap up to answer any questions that are left in the chat, and I hope you enjoy the rest of PyData Global. Bye-bye.